Good afternoon, everyone. I'm so glad that you can hear me. I want to thank you. I want to thank you for attending the 2021 MAA NAM David Blackwell Lecture. I also want to make sure to thank our sponsor, Pearson, whose video you just were able to watch and hear. My name is Omaira Ortega, and I am the president of the National Association of Mathematicians, Incorporated, also known as NAM. As such, I have the great privilege of introducing Dr. Tommy Wright, who is the 2021 David Blackwell Lecturer. The MAA NAM David Blackwell Lecture was started back in 1994 with an inaugural address by Dr. David Harold Blackwell himself. Dr. Blackwell is arguably the most decorated African-American mathematician. At the age of 16, he entered the University of Illinois at Champaign-Urbana, where he received his Bachelor's of Arts degree in 1938. And so he only took 3 years to get that bachelor's degree, even though he was just 16 years old. A year later, he received his master's in 1939, and 2 years later, his doctorate. All three of these degrees in mathematics. And that is no easy feat. Recognizing this brilliance, the Institute for Advanced Studies offered him a postdoctoral fellowship after he received his PhD, and he later held positions at Howard University and the University of California at Berkeley. Dr. Blackwell is best known for the Rao-Blackwell theorem in statistics. And though Blackwell did not originally intend to become a researcher when he first enrolled at the University of Illinois, he had this expectation of becoming an elementary school teacher, in fact. And in an interview, Blackwell stated, "I'm not interested in doing research, and I never have been. I'm interested in understanding," which is something quite different. Each year, NAM invites a mathematical researcher who exemplifies the spirit of Blackwell in both personal achievement and in service to the community. This year's David Blackwell Lecturer is Dr. Tommy Wright, who has worked in service of our nation's democracy for almost 3 decades as a research mathematical statistician at the US Census Bureau. The first census in 1790 was a simple population count, and since then, the data collected and the techniques used by the Census Bureau have become increasingly more complex. In his time at the Census Bureau, Tommy Wright has provided the overall technical leadership for the Center for Statistical Research and Methodology, CSRM, which is the Census Bureau's statistical and methodological research and collaborative consulting facility. CSRM researchers apply and develop statistical methods to manage the measurement and release of data on the behavior and condition of our nation's people, places, and businesses. Dr. Wright has over 35 years of undergraduate and graduate teaching experience in statistics and mathematics at Knoxville College, the University of Tennessee at Oak Ridge, the University of Tennessee at Knoxville, and most recently Georgetown University as an adjunct faculty since 2009. He was also an ASA NSF Census Research Fellow from 1993 to 1996. Dr. Tommy Wright was born and grew up in Birmingham, Alabama. He received a bachelor's degree in mathematics from Knoxville College. He received a master's degree in mathematics from the University of Tennessee, and he received both a master's degree and his doctoral degrees in statistics from the great Ohio State University. Today, we're going to hear about some recent results in optimal sample allocation, apportionment of the US House of Representatives, and Lagrange's identity. So without further ado, I give you Dr. Tommy Wright.
Thank you very much for that invitation, Professor Ortega, and for the invitation from the National Association of Mathematicians. I am both honored and humbled by the invitation to deliver the David Blackwell Lecture this year. Also, my sincere thanks to each of you joining this lecture to share in continued recognition of David Blackwell, who lived from 1919 to 2010, an outstanding mathematician and statistician who made many outstanding fundamental contributions to several areas, including game theory, probability, and statistics. In 1965, he was recognized by election to the National Academy of Sciences. My title today is The 2020 Census, Lagrange's Identity, and Apportionment of the U.S. House of Representatives. For a very long time, I have had an interest in the three topics: the census taken every 10 years in the United States, why is counting so difficult? Understanding how seats are apportioned in the U.S. House of Representatives every 10 years, which forms the basis of our representative form of democracy. And the beauty and simplicity of Lagrange's identity and some big results that can be derived from it. I hope you might develop some interest in at least one of these three topics. The views expressed are mine and not those of the U.S. Bureau of the Census. David Blackwell. David Blackwell. And some things are worth repeating. Professor Ortega mentioned this, and I'm going to repeat it. I am not interested in doing research. I am interested in understanding, which is quite a different thing. These words are attributed to David Blackwell, as has been mentioned. Please let me repeat it yet a third time. Basically, I am not interested in doing research. I am interested in understanding, which is quite a different thing. I want to mention a few things that go on with the Census Bureau in our work and our data products. We conduct a census every 10 years to get counts of the people in our nation as called for by the U.S. Constitution. We conduct sample surveys based in probability, monthly, quarterly, and annually to estimate characteristics of the people in our nation. We conduct a census every 5 years to get counts of the different types of businesses in our nation. We conduct sample surveys, again based in probability, monthly, quarterly, and annually to estimate characteristics of the businesses in our nation. We make use of statistical methods. Joseph Louis Lagrange, who lived between 1736 and 1813, Italian descent. In 1773, Lagrange wrote down what has now called Lagrange's identity. For the ordered pairs A sub 1, B sub 1, and A sub 2, B sub 2, direct algebraic manipulation shows that if we take the sum of squares of the first components of the ordered pairs times the sum of squares of the second component of the ordered pairs minus the square of the sum of the products of the coordinates inside the first ordered pair plus the coordinates inside the second ordered pair, then that is equal to the square of the difference of the products where we have A sub 1 times B sub 2 minus A sub 2 times B sub 1. Please notice the pattern. If we go to three ordered pairs, A sub 1, B sub 1, A sub 2, B sub 2, A sub 3, B sub 3, we see how this generalizes. We now have three terms here, and multiplying. We now have the square of a sum of three products here. And we now have, whereas before we had ordered pair 1 and ordered pair 2, we now have ordered pair 1 with ordered pair 3, and then finally ordered pair 2 with ordered pair 3. We can see a pattern. Indeed, this generalizes for n ordered pairs, where we have this expression, this sum of squares times this sum of squares minus this square of the sum of products is equal to this particular sum. This is Lagrange's identity. In my mind, it's a beautiful identity, and I wish to share a little bit of that with you today. This result can be proved by mathematical induction. Notice the way this summation is written on this side of the expression here on the right-hand side. This is a drawing of Old City Hall in New York City on Wall Street from 1790. This is where the first Congress of the United States met, and it's also where George Washington was inaugurated. I have been near this place, Federal Hall. This is a drawing of the interior of that building where the Congress met, the first Congress met. This is a picture of the current Congress. Here on the right-hand side, this is where representatives meet in the U.S. House of Representatives. And on this side, this is where the senators meet for the Senate. At this location, the president is inaugurated, the most recent president. So I have seen the site of the first inauguration of a president, and I've seen the site of the most recent president of the United States. This is an interior of the House of Representatives. The Speaker sits here, and the members sit here. Apportionment is about distributing 435 seats in the U.S. House of Representatives among the states, and we do it every 10 years following the decennial census. I wish to share the results from the 2020 census and to illustrate the exact computations, and at the very end I will give a reference where you can see a full table. So if one were to take the population count for California, which is 39,576,757, that's the largest state. Texas is the next largest state. Florida is the next largest state, New York, down to Wyoming, which has the smallest population, 577,719. So order the states like this. Along the top, place the numbers 1 over the square root of 1 times 2, 1 over the square root of 2 times 3, 1 over the square root of 3 times 4, 1 over the square root of 4 times 5, and continue out until we get to 1 over the square root of 51 times 52. That's all the number of columns we need at this particular case. So we have a sort of layout of 50 rows and 51 columns. What we do is we take this population for California and multiply it by this number and place that value here. We take the population of California again, multiply it by this number and place that population here. We take the population of California, multiply by this number and place that value there. And we do that for the entire first row. We do the same thing, a similar thing for the row with Texas, the row with Florida, all the way down for every row through Wyoming. And what we get is we get a 50 by 51 matrix of values called priority values. And the current method, which we will talk about, says do the following. First of all, the Constitution says that each state will have 1 representative in the U.S. House of Representatives. So that means that 50 seats are already allocated from the beginning. The size of the current House calls for 435 seats. So 435 minus 50 leaves 385 seats to be allocated among the 50 states. And how do we do this? Well, if one notice, first of all, that these numbers go from largest to smallest, and likewise here, these numbers go from largest to smallest. So the methodology says, look for the largest 385 numbers inside this table, the priority values, because this is the largest value in this row, and this is the largest value in this column. This will be the largest value. So the 51st seat goes to California. The next largest value is this value, and it goes to Texas. The next largest value in this table is associated with California, and the 53rd seat, in a sense, goes to California. The next largest value in this particular table is associated with Florida. The next largest value is associated with New York. So one proceeds through this table, and what you'll notice is that the way I've laid it out, the largest values will tend to be in the northwest corner of this table. So there's a sort of clear pattern as to how one can achieve this. And in fact, if we go if we complete that exercise, the 433rd seat goes to California, and in fact, the 435th seat actually goes to Minnesota. It's not shown here in this particular table. So what do we do next? We then count the number of times a state, for example, California achieves an allocation of a seat, the 51st, the 53rd, the 57th, and if we had the entire table, we would see that this happens 51 times. But California had one seat to begin with. So the total number of seats that California would get would be 51 plus 1, which is 52. And in fact, the total seat assignments are given here. So similarly, Texas, if one were to count along this row, how many times Texas would be allocated a seat according to the sequence that I just mentioned, it would be 37 plus the 1 makes a total of 38. What we see here on the very bottom row for Wyoming, Wyoming does not pick up an additional seat by marching through this particular table. So its allocation of seats for 2020 is just 1 plus 0, which is 1. And so this is the way the seats are apportioned in the House of Representatives. And at about this time, when I talk about this topic, people say, how does that work? That's the basis of much of the remaining of the talk. But this is exactly how the allocation was determined for 2020. And just to give you a taste of this, the state of Alabama, which is where I was born and grew up, received 7 seats based on its population from the 2020 census. I have lived in Tennessee. It received 9 seats. I have studied in the state of Ohio, 15 seats. I've also lived a little bit in Massachusetts, 9 seats. I've lived a little bit in Virginia. It received 11 seats. And I currently live in the state of Maryland, which received 8 seats. And you can see alongside the seats the populations from the 2020 census. The outline of my talk is to 3 parts: an introduction on apportionment. I will talk about the method that I just described in that example. It is referred to as the method of equal proportions. And I will talk about a little bit about the method prior to equal proportions, and I will talk about the transition from major fractions to equal proportions. And then the talk will end. Article 1, Section 2, Clause 3 of the United States Constitution. Representatives and direct taxes shall be apportioned among the several states which may be included within this union, according to their respective numbers. Whole numbers of free persons, 3/5 of all other persons. The actual enumeration shall be made within 3 years after the first meeting of the Congress of the United States. So this is being written in 1787. So 3 years would mean we're going to conduct the first census in 1790. And within every subsequent term of 10 years, in such manner as they meaning Congress, shall direct by law. So this is why we do the census every 10 years. The number of representatives shall not exceed 1 for every 30,000. So this is an important thing to remember. But each state shall have at least 1 representative. And until we do this enumeration in 1790, so remember this is 1787, until we do this first enumeration, the state of New Hampshire shall be entitled to choose 3, Massachusetts 8, Rhode Island and Providence Plantations 1, Connecticut 5, New York 6, New Jersey 4, Pennsylvania 8, Delaware 1, Maryland 6, Virginia 10, North Carolina 5, South Carolina 5, and Georgia 3. And so you see the very first apportionment of the seat in the House of Representatives is actually spelled out explicitly in the Constitution. If you were to count these seats that were assigned, they total to 65. You might ask, why 65 seats in the Constitution for the initial House of Representatives? Well, prior to 1787, the Articles of Confederation permitted each state between 2 and 7 members when the states met as the Continental Congress. Thus, the Constitutional Convention worked with a total representation between 26, so that's 2 times 13, 13 states, and 91 for a high, 7 times 13. For the Constitution, it was decided that each state would have 2 senators, meaning a total of 26 senators. So wanting to keep the total not to exceed 91, we have 91 minus 26 for the senators, equaling 65 members for the House of Representatives. So this is an explanation as to how the number 65 was determined for the very first House of Representatives. By the way, I should mention, I will be referring a bit to things from history, and you may think that I know great details about history. That is not the case. I know just enough for this talk, but I'm not an authority by any means. And some of the things that I will share, I am in the process of documenting more carefully. So I want to make that caution aware. How about the apportionment of the 65 seats? How was that decided? Let P sub I be the population of state I. This includes 3/5 times slaves, estimates from state assessments and state censuses, and let P be the sum of P sub 1 through P sub 13. And so the various states showed up at this meeting and brought some numbers, and they were not sure the quality of these numbers varied, and that's why the idea was that in the future we're going to do this on an actual enumeration, and we're going to do it every 10 years. But initially, people showed up with these particular counts, and so you will see that Maryland, for example, had 222,000 population, and the idea is that this population divided by the overall population times 65 meant that Maryland's share of the 65 seats was 5.855. Virginia's share of the seats was 12.6598. So these were the numbers in terms of shares, but what actually happened after much discussion is that the assignment of seats, which I just read for you from the Constitution, is 3, 8, and so on. What you'll notice from this table is that Virginia, being the largest state at that time, received 10 seats in the original House of Representatives, and Georgia, which is the smallest state in this list, received 3 seats in the House of Representatives. This is noteworthy because Rhode Island, for example, which is twice the size of Georgia, received only 1 seat. I should also say that it is well known that Rhode Island was not in attendance at this meeting when this discussion, it boycotted the meeting because it wanted to get more power and control for the states rather and less central control. So the lesson from this is that if you miss the meeting, you might miss out on representation. What about the apportionment following the 1790 census? 2 leading methods were considered, one promoted by Thomas Jefferson and another one promoted by Alexander Hamilton. The Jefferson method, roughly, step 1, choose the house size. Step 2, find the divisor so that the whole numbers contained in the quotients of the states sum to the chosen house size. And number 3, give to each state its whole number of seats. I will illustrate these. Hamilton, choose the house size. Find the proportion, that is the share, and assign whole numbers of seats to each state. For the moment, ignore the fraction. And then there is a second step, assign the remaining seats to states with the largest fractions. This here, Jefferson procedure seems to be done with 1 step. You divide once, and then you look and see what the representation will be for each state. But with Hamilton, there appear to be 2 steps. This will be crucial in a moment. So if we look at Jefferson's plan closer, 105 seats was the number. The divisor happened to be 33,000. So I would like to walk through the row with Maryland to discuss what's in this table. So in the first column, this number represents the total population from the 1790 census of free population in the state of Maryland. This number represents the size of the slave population in the state of Maryland from the 1790 census. If you add these 2 numbers together, one gets 319,728. But this is not the number, this is not the population that was used to apportion the seats in the House of the 105 seats, or at least in this plan. This number, according to the Constitution, was reduced by 3/5. So we take this number, multiply by 3/5, then add to this number, we get this number, which is the actual apportionment number. And you will see that a similar thing is done for each of the states. That is, the actual slave population is not used, it's actually 3/5 of that number. And so these are the numbers that form the apportionment population to determine the assignment of seats. So what you see is that this number for Maryland, if we take this number and divide it by 33,000, then we will get 8.440. And according to Jefferson's plan, just look at the integer part, which is 8. Similarly, North Carolina, if you take this population and divide by 33,000, we get 10.713, but we only look at the integer part and it's 10. And this is done in such a way that the integers sum to 105. Notice that in this particular case, if you look at the total population without adjusting for slaves, the population of the North is pretty much the same as the population of the South. But because of this, because of this reduction in the slave population here, you'll see what happened. The South had significant, I would say, significantly less representation in the House of Representatives. Another thing I wish to point out is that if you were to take this population and divide by 14, which is this last column, this represents the number of people per representative, 33,952. All of these numbers represent 33,000. So as far as the Constitution's requirement that the number of representatives not exceed 1 for every 30,000 people, this is just fine. This is satisfying. On the other hand, Hamilton's plan called for 120 seats in the House of Representatives. And how do we get this 120 seats? We take 30,000 and divide by the apportionment population, which we discussed in the previous table, and you'll get roughly 120 seats. What do? We take a share. So we take, for example, let's go to Maryland. We take Maryland's population divided by the overall population and multiply that times 120. And the share in this particular case is 9.243. We take the integer part, which is 9. We do the same thing for North Carolina. We get 11.732. We only look at the integer part. So by doing this for each of the, by the way, there are 15 states here. So actually Vermont and Kentucky have been added at about this time for 1790. This sums to 111. So you have to ask yourself, well, I thought the size of the seat is 120. So what about the remaining 9 seats? To get the remaining 9 seats, Hamilton says, look for the largest fractional part. So the largest fractional part is with New Jersey. So this 5 turns into 1 additional seat, which is 6. The next largest fraction is with Virginia. And so this 20 becomes 21. And we proceed in that way 9 times until we get to 120. This is Alexander Hamilton's plan. What you will notice is that if we take this population, for example, for Massachusetts, and divide by 16, then we get 29.708. This is a state where 1 representative represents less than 30 people. So this is a violation of the Constitution. That is, the number of representatives shall not exceed 1 for every 30,000. This is violated here. It is violated with Connecticut, New Jersey, New Hampshire, Vermont, North Carolina, South Carolina, and Delaware. But still, it passed the 2 houses. So the Hamilton plan was acted upon first, and it passed the 2 houses. Some argued for the 120 representatives, Hamilton plan, some for the 105 representatives. Washington said no to the 120 representative plan of Hamilton. In fact, this is the first presidential veto in our country's history over apportionment. Washington eventually said yes to the 105 representatives by Thomas Jefferson. And here are the wordings of Washington's veto. And this is directed at Hamilton's plan and to the House. United States, April 5th, 1792. Gentlemen of the House of Representatives, I have maturely considered the acts passed by the 2 houses entitled An Act for Apportionment of Representatives among the several states according to the first enumeration. And I return it to your House wherein it originated with the following objections. First, the Constitution has prescribed that representatives shall be apportioned among the several states according to their respective numbers. And there is no one uniform proportion. Remember, there are two steps with Hamilton's plan. There's no one uniform proportion or divisor which applied to the respective numbers of the states will yield the number of allotments of representatives proposed by the bill. Second, the Constitution has also provided that the number of representatives shall not exceed one for every 30,000 people, which restriction is by the context and by fair and obvious constitution to be applied to the separate and respective numbers of the states. And the bill that I have before me, Hamilton, which calls for 120, has allocated to 8 of the states more than one for every 1,000. So it's very clear why this veto is coming from the president. Now I would like to move to apportionment a bit more in general. We want to distribute 8 seats in the U.S. House of Representatives among states based on population. Right now, this number is 435. If a state's share of the 8 seats is not a positive integer, what about the fractional part? Should one round up, down, or not at all? Fractional parts have been a concern since 1790, and there's a wonderful book which I would commend to people by Belinsky and Young. The current method is the method of equal proportions, used every 10 years since 1940 census to distribute 435 seats in the U.S. House of Representatives among the states. Other methods have been used prior to 1940. All have advantages as well as limitations. To get a taste of what's going on, if we look at the share, so this is the population of Alabama divided by the total population. If we look at the share from the 2020 census of Alabama, we get 6.608. The share for Maryland, 8.126. This is the share of the 435 seats, if we do this computation. The share for New York, 26.559 seats. The share for Minnesota, 7.501 seats. And the share for Rhode Island, 1.443. So what might we do? One might say, well, we should round these numbers to the nearest integer. You might think this would be 7, this would be 8, 27, 8, and 1. What actually happens with the method of equal proportions is that this becomes 7, this becomes 8 so far, but this, only 26, this 8, this goes all the way up to 2. So one might say, well, I want to know more about this methodology. Okay, let P sub I be the number of people in state I, let H sub I be the number of seats to assign to state I, let P, as before, be the sum of the P sub I's. Now this has 50, and let H be the total number of seats in the U.S. House of Representatives. There is this idea of number of people per representative. If we look at a national level, this would be the total population of the country divided by the total number of seats in the House of Representatives, which is now 435. If we look at this at a state level, by each state level, the population for state I divided by the number of seats in the House of Representatives state I. We want these proportions to be the same. We want each of the states to be the same, all of these, but we also want them to be equal to the national level. That is what we would like to have. Building on the work of Hill in 1911, Huntington in 1921 took the fundamental principle as follows. For any states I and J, the total population of state I divided by the number of seats for state I should be as nearly equal as possible to the population of state J divided by the number of seats assigned to state J. This is the goal. This is the fundamental principle. Huntington's definition of inequality was relative difference. That is, how would we measure the closeness of these two ratios? We would measure it by taking the absolute value of their difference and dividing by the minimum of the two ratios. This is Huntington's definition of inequality, how to measure closeness, and also the idea coming from Hill. Huntington's precise formulation of the problem is as follows. Postulate 1. For two states I and J, the relative difference between this ratio and this ratio should be as small as possible. Postulate 2. In a satisfactory apportionment, there should be no pair of states which is capable of being improved, that is, made closer by a transfer of representatives within that pair, and that is by looking at the relative difference to make it smaller. These postulates lead to the following theorem due to Huntington. For any given values of P sub 1 through P sub 50, and I'm using P 50 now because we have 50 states, and H, which is the size of the house, there will always be one and only one satisfactory apportionment in the sense defined in postulates 1 and 2. And he states this as we have stated in the example at the beginning. First, assign one representative to each state. Then compute an array of so-called priority values where each row corresponds to one of the states. And so in our computation that we did at the very beginning, this piece of 1 is the population of California times 1 over the square root of 1 times 2, and so on. So this is actually a generalization of what we did in our example at the very beginning. Pick H minus 50 largest priority values. So in this particular case, this is the 385 with the associated states. Each state gets an additional seat each time one of its priority values is among the H minus 50 largest values. So this is the method of equal proportions. Huntington states a solution building on Hill and gives what I would say is an indirect proof of its optimality. We seek an alternative direct derivation which seems clearer and more insightful, at least to me. So the alternative derivation comes in 2014, motivated by Huntington's formulation for fixed P sub I and P sub j and the constraint that the total number of seats should sum to H. We want to determine H sub I and H sub j for all 50 states so that these ratios are equal. That is what we would like. That is what we would like to do. Each representative should represent the same number of people. Equivalently, for all I and j, then this equation, imagine a factoring the denominator H sub I into the square root of H sub I times the square root of H sub I, and in this particular denominator, factor H sub j into the square root of H sub j times the square root of H sub j. If you do that, then this equation can be written as this equation. It can be written as this equation. Equality is rarely possible. We would like for this to be equal to 0 for all possible pairs of states. So this is the binomial coefficient 50 choose 2. Thinking of 3, that is this quantity, leads us to determine the H sub i's to minimize this objective functions. Statisticians like sums of squares to minimize. So don't be surprised. I'm introducing this as an objective function. This is an objective function which we want to optimize. In this particular case, we want to minimize it, and subject to this constraint that the sum of the seats should sum to H. Recall Lagrange's identity from 1773, which I mentioned at the beginning of the talk, and you'll see this summation here on this right-hand side, and you also kind of see it on this right-hand side. And so if you have a good memory, you might say, this might there might be some value in using and appealing to Lagrange's identity. By taking A sub I equal to the population of state I divided by the square root of H sub I, B sub I equal to the square root of H sub I, and N equal to 50, then this equation becomes this equation. And the interesting thing about this equation is that this equation has in it on the right-hand side the objective function that we would like to minimize. And in fact, we will focus on this for much of what I'm going to say remaining, but we will look at the left-hand side. So it is the left-hand side that we will find that we can work with in order to minimize the right-hand side. So before that, I want to call to your attention a result due to ons. Suppose you have a positive integer, H sub I. If we take 1 minus 1 over H sub I, it is equal to, here's the 1, and here's the minus 1 over H sub I. So in the middle, just add 0, but in the form 1/2 minus 1/2. Add another 0, but in the form 1/3 minus 1/3, and so forth here. Then if we regroup with the 1, the negative 1/2, with the 1/2, the negative 1/3, and so on, what we get is that we can rewrite this as 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, and so on. And we see if we solve for 1 over H sub I, it gives this result. This is just solving this equal to that for 1 over H sub I. So going back to the objective function that we want to minimize and using Lagrange's representation of this, so now looking at this, what we see is that this sum of h sub i's is equal to h. This sum of p sub i's is equal to p. If we substitute in for 1 over h sub I, the expression that we just observed, then this expression now becomes, we can regroup things by pulling this p squared over here, distributing p sub I squared through this difference, this expression, and running the summation sign through. I realize there's a lot going on here, but the main idea is to show at a high level what's going on. What we notice is that this part of the expression, remember this is the objective function, and it is equal to this. This part is a constant. There are no h sub i's here. And so any attempt to minimize is going to occur here. It's going to, and what we notice is that this is a sum of 50 sums. And so I want to write it out like this. So the objective function, which we're trying to minimize, is equal to a constant, which has nothing to do with h sub i's. And what we see here is this is kind of a, this first row here, this part of it is with the first state. You can think of New York if you like. This is with the second state. And what you see is that we are subtracting these positive numbers from this quantity which we're trying to minimize. And to some extent, this sort of says, New York, you have 1 seat. If you subtract this quantity, you will now have 2 seats. If you subtract yet another quantity, you have 2 seats, you will now have 3 seats. So in a way, this looks like we have, and what you see is at the very end, when you stop subtracting, you have h sub 1, which is what you would like to have. When you stop here on the second row, you have h sub 2. So this gives kind of a layout of how one can determine h sub 1, h sub 2. So the question is, if I'm going to minimize this, what numbers do I want to subtract from this? Do I want to subtract small numbers, or do I want to subtract the larger numbers? Before that, take one more look. Note that the amount by which this objective function decreases if we increase the number of representatives in state I from h sub I minus 1 to h sub I, it happens to be this. It happens to be the very terms, the kinds of terms that we see on the, it's the very kinds of terms that we see on the previous page. So this is telling us as we increase seats terms from a given state, then this is the amount by which this is decreasing, which is what we want to happen. We want to minimize our objective function. Another thing, the expression that's a constant part of that is fixed, and it is the value of our objective function when h sub I is equal to 1 for all of the i's. So this is the objective function. If we place in 1 for each x, we get this quantity here. I think it's very easy to see it from here. It is also the maximum value for it. So this is the maximum value, and what we're doing by each of those subtractions is we are making this maximum smaller and smaller and smaller and smaller, but with a constraint. So it's important to keep in mind that there is that constraint. So finally, if we look at this objective function, it is equal to this constant minus these things. We will minimize this overall objective function if we pick the largest terms. It is the largest terms that we want to pick one by one out of this in the overall sum subject to the constraint. That is, when each state is assigned 1 seat in the U.S. House of Representatives, that's on the first step, and each state receives an additional seat each time it has a term which appears among the h minus 50 largest terms. Now notice that in the table that I used, I did not have h's. So these h's are in each of these terms. So in terms of minimizing, they don't matter. The h's, I can ignore the h's. And also you remember that in the algorithm, I had square roots in the denominators. And also the p's in the numerators were not squared. So if we just take square roots, we will get exactly what we have. If you have a is greater than b, then a square is great. It goes both ways. So by taking square roots, we do not change the order at all. So a formal statement by 1921 of Huntington of his algorithm is given here, as we have said before. First, assign one representative to each state, compute an array of priority values like this, go through this, and get the remaining 385 now, because H is now 435 seats. This ends the derivation of the method of equal proportions. To illustrate the equal proportions optimality, this is one of the postulates, postulate 2 of Huntington. So let's take 2 states, Virginia and Washington. This is the population from the 2020 census of Virginia. This is the population from the 2020 census for Washington. According to the method of equal proportions, Virginia is assigned 11 seats, Washington is assigned 10. If we look at the measure of closeness, what we get here, relative differences, for this situation, we get 0.01968. That's a measure of how close this ratio is to this ratio. It's a relative difference. So can we get these ratios closer? And so plan A would mean, well, let's see. Let's take 1 seat from Virginia, it becomes 10, and let's give it to Washington, it becomes 11. If you go through and perform the calculations again, and this is mainly arithmetic, the measure of closeness becomes 0.23381. It's larger than the method of equal proportion. Well, what's the other option? If we were to take 1 seat from Washington, Washington becomes 9, and give it to Virginia. So Virginia's number of seats would become 12. Would this representation make this measure of closeness smaller? Not smaller than this. It's 0.18873. So this is what is meant by. This happens for this ordered pair, but it happens for all binomial coefficient 50 choose 2 ordered pairs. I think it's quite a result. It's quite a result that you cannot, with the method of equal proportions, make the relative differences any smaller. It's quite a result. What criterion to use to apportion the house? This topic is of considerable mathematical interest and controversy. Seemingly, and you saw the controversy at the very beginning between Thomas Jefferson and Alexander Hamilton, seemingly equivalent criterion can lead to quite different methods. For example, suppose we were to switch the p sub i's and the h sub i's, that is, what we've talked about so far with the method of equal proportions is trying to make equality here. But suppose we have h sub I divided by p sub I. So this is the representation per person. This is the number of people per representative. And you might say, well, this criterion seems to be the equivalent to this, and so maybe I get the same result. You might think that. Well, following through with the analogous details leads to choosing h sub I to minimize this objective function, where now the h's and the p's have switched places. And we still have that constraint that the sum of the h sub I should sum to 8, and we want to determine h sub I and h sub j. We get an array of numbers. I'll not go through the details here. I will just mention that the method is called the method of major fractions. This happens to be the method that was used prior to the method of equal proportion. I will not take the time to go through it, but it can be displayed in a similar way, but you don't see square roots, and the rules are a little bit different. You do have this idea that each state does still get 1 representative for sure, as called for by the Constitution. But then the question is, how do you determine the remaining 385 seats? Well, in 1910, the method of major fractions was used. And what you see is here in New York had the largest population, 43 seats, and you see it for all. There were 46 states at the time. The size of the house was 433. At about 1910, the country started looking more seriously at the mathematics behind the method of apportionment, and several people got involved, including someone from Cornell by the name of Wilcox, including a statistician at the Census Bureau by the name of Joseph Hill. So this is where the Hill comes up. And so Hill proposes a method in 1911, following the 1910 census. And in 1920, the country has two methods which are getting considerable attention again: the method of major fractions and the method of equal proportions. And by the way, the Hill method, Hill collaborated with Huntington, and Huntington published results leading what he called the equal proportions. So at about this time, we have two methods that are up for consideration. What you'll see here is that under the method of major fractions, New York gets 43, equal proportions says 42. North Carolina gets 11 under one, 10 under another. Virginia gets 10 under one, Virginia 9 under another method. Rhode Island gets 2 seats under one of the techniques and 3 under the other. New Mexico gets 1 and then 2. Talk about controversy. So the question, so you can imagine the census is completed, and Congress is trying to decide how to allocate the seats in the House of Representatives. This led to great controversy. There was also another thing that led to great controversy. There were several, but 2 leading reasons. The 1920 census was the first census that showed for the first time more people were living in urban areas than in the countryside. So for these 2 leading reasons, along with other concerns, there was no apportionment in 1920. That is, the country experienced what some might call a constitutional crisis. The Constitution said we're going to do this every 10 years, and there was no apportionment. So the country went along throughout the decade without reapportioning the seats in the House of Representatives. The apportionment from 1910 was the one that was used throughout 1920. There was something done in 1929. I'll not go into that, but there was great discussion throughout the decade, the 1920s, what to do. And mathematicians, statisticians, and economists got involved quite a bit. In 1930, looking at the 2 methods, the apportionments turned out to be exactly the same. So there was no controversy. No controversy at all. Always peaceful, you could say. Well, in 1940 census, the 2 methods differed for 2 states, Michigan and Arkansas. Michigan received 18 from one method, 17 from another. Arkansas received 6 from one and 7 from the other. This led to controversy. What to do? Equal proportions becomes official and fixed, and much of this is due to the discussion in the 20s and additional work. November 15, 1941, equal proportions is fixed into law. President Roosevelt signs House of Representatives 22665, Public Law 291. Apportionment of representatives in Congress. Be it enacted by the Senate and the House, both passed. Section 2.28, on the first day or within 1 week thereafter of the first regular session of the 82nd Congress and of each 5th Congress thereafter, the President shall transmit to the Congress a statement following the whole number of persons in each state and the number of representatives to which each state should be entitled, under an apportionment of the then existing number of representatives by the method known as the method of equal proportion. No state to receive less than 1 member. This happened in our country in the month of April this year as a result of the 2020 census, which was conducted last year. Thank you very much for listening to the talk. I wish to just mention a few references here. Belinsky and Young, this is a book. If you Google their names, Fair Representation. If you want to look at the original ideas of equal proportion, there is this citation by Hill. Huntington has 2 papers, in one 1921 one 1928. And if you want to look at the entire big table that I just talked about, if you were to Google the words demystifying apportionment, you would probably be led to this a very big table in a newsletter which I just shared, so you could get all of the details and all of the arithmetic that you'd like to have. Well, thank you very much for listening. That concludes my talk.
Thank you so much, Dr. Wright. Um, I don't think we have time for questions, actually. There are, it's about a couple minutes before the next session starts. And honestly, the questions that I saw in the chat, you were able to answer in your talk. So I don't know if you were following the chat.
I am not. I was not.
So you're psychic. That's great. But
I was not. Go ahead.
But I hope that you're following the chat now, because there's applause and thank yous. You know, because we're a virtual audience, we rely on the chat. So thank you so much.
I want to thank the audience. I thoroughly enjoy this topic, and it is a topic that has interested mathematicians, not so much statisticians. So I'm trying to get some of my statistics colleagues a bit more interested in this. And I would commend it to anyone in the audience to take this up, particularly if you're in an undergraduate course and you're looking for a course to offer during the winter term. That little book by Belinsky and Young is just ideal to get you started. But I find it a very fascinating topic.
Okay. Well, thank you so much, Dr. Wright, for being the 2021 David Harold Blackwell Lecturer. NAM is so thankful for your taking the time to give this lecture, and we also, the MAA also thanks you on this for being our joint MAA NAM Blackwell Lecturer this year.
Thank you very much.
Mm-hmm.